In this video lecture, let me discuss the types, synthesis, properties, and applications of carbon nanotubes. Carbon nanotubes are cylindrical nanostructures made of carbon atoms arranged in a hexagonal pattern. They have an extremely high length to diameter ratio. CNTs are known for their exceptional mechanical strength, high electrical conductivity, and excellent thermal properties. These features make them valuable in nanoelectronics, energy devices, composites, and biomedical applications. Types of carbon nanotubes: single walled carbon nanotubes, multi walled carbon nanotubes. Single-walled carbon nanotubes are formed by rolling a single graphene sheet into a seamless tube. Its diameter around 1 nanometer and length can be several micrometers. Their electronic properties depend on how the sheet is rolled. Based on the arrangement of carbon atoms, they are classified as armchair, metallic conductor, zigzag, can be metallic or semiconducting, chiral, generally semiconducting. Armchair model: the carbon atoms are arranged so that the tube edge resembles the arms of a chair, creating parallel rows that make the tube metallic. Zigzag: the carbon atoms are arranged in a pattern that forms a zigzag edge around the tube, and this geometry can produce either metallic or semiconducting behavior. Chiral: the carbon atoms are arranged in a twisted spiral pattern along the tube, giving a helical structure that makes the tube mostly semiconducting. Chirality decides whether a single-walled carbon nanotube behaves like a metal or a semiconductor. Multi-walled carbon nanotubes consist of multiple graphene layers rolled into concentric or spiral tubes. Two models describe their structure: Russian doll model, parchment model. Russian doll model: several tubes placed one inside another like nested cylinders. Parchment model: a single graphene sheet rolled many times like a scroll. Multi-walled carbon nanotubes usually have larger diameter and higher mechanical strength compared to single-walled carbon nanotubes. Most important and essential properties of CNTs include very high mechanical strength, stronger than steel; excellent electrical conductivity, it's either metallic or semiconducting; high thermal conductivity along the tube; lightweight due to hollow cylindrical structure; high aspect ratio. Synthesis of carbon nanotubes: there are three methods which include arc discharge method, laser ablation method, chemical vapor deposition. Arc discharge method: a high temperature electric arc is formed between two graphite electrodes in an inert gas. The arc vaporizes carbon. The carbon vapor cools and forms CNTs along with other forms like fullerenes and amorphous carbon. Advantages: high crystallinity, good quality carbon nanotubes. Disadvantages: lower yield, needs purification, high energy consumption. Mostly produces multi-walled carbon nanotubes, but single-walled carbon nanotubes can be formed if metal catalysts are added. Laser ablation method. A high power laser pulses onto a graphite target containing metal catalyst. The intense heat releases carbon atoms which recombine to form CNTs. Conducted at around 1200 degrees Celsius in a furnace under inert gas flow. Produces high purity single walled carbon nanotubes but is expensive and less suitable for large scale production. Chemical vapor deposition. Hydrocarbon gases like methane, acetylene, or ethylene are introduced into a furnace. Metal nanoparticles act as catalysts at temperatures of 600 to 900 degrees Celsius. The hydrocarbon decomposes and carbon atoms deposit on catalysts growing CNTs. Advantages: low cost, scalable, high yield, widely used for industrial CNT synthesis. Applications of carbon nanotubes: nanoelectronics, CNT-based transistors can switch extremely fast and operate at room temperature. CNT memory circuits and interconnects reduce device size and power consumption. Energy devices, paper batteries, CNTs embedded in cellulose act as conductive flexible electrodes. Supercapacitors, aligned CNTs provide high surface area and fast charge discharge ability. Solar cells, CNT fullerene tubes improve electron transport in organic solar cells. Composite materials, CNTs significantly enhance the strength, stiffness, and durability of polymers used in aerospace parts, sports equipment, and lightweight automobiles. Protective clothing. CNT reinforced fibers show high resistance to impact, making them suitable for stab-proof, bullet-resistant materials. Biomedical uses. CNTs are similar in size to proteins and DNA, making them useful in biosensors, drug delivery, and tissue engineering. Thank you for watching this video lecture.